I'd like to welcome everybody to this next presentation in the Community of Practice webinars. The Risk-Informed Performance-Based Principles and Policy Committee, RP3C we call it, of ANS has been putting on these events for the past 5 years. Presentations and recordings of the event are available to the public at the ANS website under the tab RP3C. There are now almost 50 such recordings available. The purpose of these webinars is to offer practitioners of concepts and methods related to risk-informed and performance-based approaches, RIPB we call it, a chance to share their knowledge and experience. I would expect that such practice is used for implementing nuclear technology and evaluating its effectiveness. The purpose of RP3C is to help modernize ANS standards. The Nuclear Energy Innovation and Modernization Act of 2019 associated modernization with application of RIPB approaches. Congress reiterated and reinforced this idea to achieve effective regulation and oversight in the Advance Act of 2024. There is growing realization within the nuclear community that conventional, prescriptive, and deterministic approaches are not going to support increasing use of nuclear technology to play its rightful role for the benefit of society. Socializing alternative approaches could drive changes in industry and regulatory practices. ANS offers the COP files on its website to serve as a knowledge repository of the experience from a wide range of practitioners in the field. We hope that more people will use this knowledge base to speed up needed changes in the state of the art as well as the state of practice. These events are generally scheduled on the last Friday of a month. Today is an exception, and we will hear from Paul Amico, who will introduce himself with his background and the presentation he is about to make. Paul, welcome. Go ahead.
Okay, well, hello everyone. I'm Paul Amico. Yes, I have. I'm closing in on 50 years in the business. I am a nuclear engineer. Started in the risk world right after WASH 1400, and so I'm going to talk a little bit about this concept here, and just to give a little bit of background on it. This has evolved and has refined, and it really kind of goes back to two papers that I wrote in the early 90s for a couple of conferences with my colleague John Young when we were working on a program DOE was planning to build an MHTGR. And that's where the concept came from, and it's just evolved over the years, and EPRI's done various things on it also, and it's just kind of really gotten to the point now that it's really matured. I'll give a quick introduction to JENSEN HUGHES, just to say that we're at this global firm. We do a lot of risk type work, and we type it. It's all different types of facilities. Essentially, it can be any kind of facility, and risk-informed performance-based drives our whole company. We use it for non-nuclear energy facilities. We use it for process facilities. We use it for health care facilities. We basically use it for all kinds of different things. And as Prasad was saying, trying to find other and better ways to achieve the intent of the codes and standards rather than just going and blindly meeting them. So we want to be purposeful and efficiently ensuring regulatory compliance and risk reduction with respect to safety, security, and operational resilience. So that's a little bit about the company. You can see some of the things we do. So what's driving there's a lot of interest in this now, in this whole concept of risk-informed performance-based design. And who's really driving it? What we've seen in our discussions is it's really the off-takers that are driving this. It's the Amazons and the Microsofts and the Dows and those people. They're the ones that are driving this because they need to have energy supplies that are reliable. A lot of these data centers want to be behind the meter. If obviously, if they have a issue with availability or capacity factor, they got to buy replacement power, and it can be very expensive. For Dow, if it goes down and they lose their steam, and they've got to generate steam and fire up some of their old oil-fired plants or gas-fired plants, you know, this is very important to them. They're not these people are not worried about safety. I don't mean they don't care. They're just not worried. We've sold that. They look at this and they go, they are convinced nuclear is safe. They're convinced it's low carbon. They're convinced it's, you know, good for the environment. What they're not convinced of yet is whether they can get the kind of reliability they need if they're going to invest in these as their energy source. So there needs to be a balance that optimizes both the safety goals and the production goals, and a risk-informed performance-based approach is really the best way to do that. And the principle behind it here, one of these is from an EPRI document, one of these is from an NEI document, these two things. And what have been found, and you can see these are relatively recent documents from 5, 6, 7 years ago. And as you can see, what's happened over time is as safety has improved, risk has gone down, guess what? Capacity factors have gone up. So, and so you can see what's been determined in the NEI document, this nexus between safety and operational, is that a plant that operates better is also safer. And there's a direct correlation between being safe and being good in operation. So what do you need to do if you're going to use this particular approach? So the first step is to establish performance goals. And so the first type we're going to talk about is quantitative performance goals. And you need, again, to have a balance between safety and productivity when you're doing that. The starting point is to establish it for both at the plant level. We have been using traditionally core damage frequency and large early release for light water reactors. That's a typical safety one. When it comes to the more advanced reactors, we're looking at other things. And then availability factor and capacity factor are typical productivity performance goals. And we want to provide this match between the plant level goals and the design process. And in order to do that, we use two tools. One is PRA. I'm sure everyone on this call knows about that. And the other one is something called generation risk assessment. And these are used to allocate the goals at a lower level. We basically at the function, system, and component level. And the level of the goal will depend on the status of the design process. And we'll get a little bit more into that pretty soon. The other thing is that not all goals are quantitative. There really do need to be qualitative and safety and production goals. They have their place. Although they're qualitative, they're still, in our minds, really, they're still probabilistic. The goals themselves are risk-informed. They're based on an understanding of their value in risk space. But there's something that they're the things that really don't fit into this quantitative modeling. So qualitative performance goals, they're related to specific functional, operational features that have proven over time, because we've done risk studies on them, that they have associated with them an acceptable level of performance. In order to use a qualitative goal, though, it has to be clearly stated in an unambiguous manner. This is what you need to achieve. Not necessarily how, but what. And they're related to all these different aspects of the design: physical design, functional design, all the administrative features, and you have to be able to measure and verify them by inspection, testing, or analysis. And so some of them, they really do, in fact, imply certain likelihoods of occurrence. The single failure criterion, right? You know that if you don't have a single failure, you are going to have a lower likelihood of occurrence. Functional diversity is lower than just having redundancy. Alternate operating modes, ways in which you can compensate for a functional deficiency in one area by doing something else. Physical separation, equipment redundancy, and then functional backup, a different way to perform the same function. So the point here really is that although these are qualitative goals, they are known from our experience to reduce the probability of system and function failure. So we don't want to ignore these. Again, this is part of a risk-informed process. We're not just going to use numbers. We're going to use other aspects also. So what's the process that we would go through? So in order to strike that balance, you have to have a well thought out, risk-informed, performance-based design process. This particular flow chart shows the concept of how we approach this. And what I'm going to do is I'm going to break this down, and we're going to kind of go through the different pieces of this and see how this process works. So to start off with, we're going to design a plan to deterministic design criteria. You know, it's not, we don't design to risk. We don't do a risk assessment and design the plan. We have to start with something. So we're going to pick well-known, well-respected, well-used deterministic design criteria, and we're going to put together a baseline plant design to start from. Once we have that design, we can then look at it in a risk-informed, performance-based framework. So the next piece here then is to say, okay, I have a design and I have quantitative goals for both safety and for production. And so we know from past experience, examples, plants were designed, nuclear plants were designed very strictly to deterministic, restrictive criteria for many, many years, and we started doing PRAs really, well, we started in the 70s, but we started really doing them in earnest in the 90s, and we found out that just meeting deterministic design criteria didn't necessarily mean that you were going to achieve your safety goals. And we didn't really study very much the reliability side of it. So the first area here, which I refer to on this diagram as the inner loop, is take the design and ask the question, do I meet both of my quantitative goals? Do I meet the safety goal and the production goal? And if the answer to that is no, then I'm going to say, all right, what is it? What is the PRA and GRA telling me about why that's the case? What are the dominant contributors to the safety or reliability deficiencies that are not allowing us to meet our goals? And at that point, then, we're going to identify design options to help us to meet those goals. And I'm going to come back to that part of the process a little bit later. But before we do that, let's just say, okay, we've now gone through this iterative process. We have achieved our goals. And the next question we're going to ask is, but is it optimized? This is when now, once the base design meets the safety and production goals, the search for optimization begins, which is driving more trade studies. And so I call this the outer loop of the process. I can say I comply with the quantitative goals, but I'm asking myself the question, could I do better? Are there ways I can make this better? And then I'm going to go and say, what am I missing from an optimization standpoint? And so I, again, identify design options, and I'm going to then go forward and start to do some of these trade studies. Well, let's look at that trade study section there. I'm going to as I'm going through the inner loop and the outer loop, I'm going to look at options for how I can improve the plant. So there's obviously going to be various ways. And regardless of which loop you come from, you're gonna have various options. So they look at these in both the quantitative and qualitative space. Because I don't want to, again, I'm not working with just numbers. I can improve, if I can improve things and I am not properly considering these other factors. And what are these other factors? And you can see I'm talking about down here. What are the other things that I consider? There's cost. Okay, that is not something I'm putting in the PRA and the GRA. It's something that comes into my decision process. What about environmental issues? I'm not quantifying those things like water usage and and air and various things like that. What about any social issues that come into play? And then another piece is the compliance with code standards and criteria. Now, if you look at one of the things that's in here, we do have it here. The question we're going to ask is, when I am looking at this optimization of the design, am I hitting my head against deterministic design criteria that are driving me to do something that maybe isn't optimal? And this is where that thing, and again, the thing that Prasad mentioned comes in. In some cases, and we've done this across many industries, in fire protection and various things, there's some cases where a case can be made that a change or an exception to a deterministic criteria will achieve the same level of safety and performance by alternate means. Okay, engineering equivalency, some people call it. There's various different terminologies. And so one of the options that exists is to take an exception. In the case of things that affect only production, that's obviously something for the most part that is a corporate decision. In things that are exceptions or relief from a regulatory requirement, you're going to need to work in the nuclear business with the NRC. Other types of industries refer to the authority having jurisdiction, whatever it may be, that you're going to go in. But that option should always exist. It should always exist to say, I can demonstrate I have an alternate way to meet the intent. I meet the what. I don't need to use your how. And so that's the process that's gone through. So a key part of this, again, is the modeling. It's the PRA and the GRA. You all know what a PRA is. So what's a GRA? Okay. So this is the process where you estimate generation loss during plant operation. And in that case, you're going to look at the probability, magnitude, and duration of plant trips or D rates due to postulated equipment failure. The GRA models potential generation and economic impact. We usually use something like megawatt hours per year. Again, in this part of it, yes, cost is an issue. Other things are an issue. But again, that's the other considerations when I'm talking about, again, design trade studies. So in this case, we're trying to look at it. It's still frequency, consequence, risk, as the same as we do in the PRA. It's a much more robust than the simplistic qualitative approaches, for example, single point vulnerability that we use, because it's more holistic. In the same way that PRA is more holistic than single failure criterion, GRA is more holistic, and because you can address redundancies, interdependencies, dependencies, diversity, et cetera, in the plant systems and components, and get an understanding of how they're helping you. And it provides quantitative estimates to support the decision making. And just like in PRA, you get importance rankings, critical components in terms of production risk. It's important to note here, by the way, that the fault and event trees that you develop for the PRA are also used in the GRA. Okay, additional modeling is required. I will discuss that later. But part of it is you're going to use the PRA models. You don't have to start from scratch and build a GRA. And in fact, one way to consider, by the way, is part of the GRA is quantifying the OK sequences in a PRA, because they may be OK from a risk perspective, but they're certainly in many cases not OK for the continued operation and resiliency of the plant. It's a piece. It's not the biggest piece, but it's a piece. So a typical flow diagram for using it is here. The center part of it is the GRA itself. So we're going to look at the production functions, those things like the power conversion system, feed water, condensate, etc. Other systems that are required, like off gas, that are required to function in order for the plant to keep producing power. And typically we'll do an FMEA on that, and that information will feed into the GRA process itself. Then you're going to have other input from various whatever sources there are of planned unavailability, repair times, failure rates, restore times, and what are the consequences, what's the D-rate level, and you're going to build this model. You have a trip D-rate model and a calculator for that, the availability model. You're going to look at this from the standpoint of efficiency, and then you're going to enter risk-informed asset management, and we'll talk about a very important part of that coming up right with the next slide, and that is RAMI. Reliability, availability, maintainability, inspectability. It's an integral element of the performance. In that flow chart I showed you before, there were inputs and outputs from RAMI into the GRA and PRA process. Because you have to have a program in order to not just to be safe, but to produce power, an effective program for reliability, availability, maintainability, inspectability. And notice that these last two in particular are very important in the design process. Maintainability, how hard is it to get into where I need to go to maintain something? I have to design that. Inspectability, how hard is it going to be to inspect something? I have to design that. So this process starts very early in the design process. It's an integrated tool. You're focused on system structures and components. The big pictures, PRA, GRA, it's going to give me importance measures, and then it's going to say, okay, now what does that mean in terms of the design of the systems and the specifications for the equipment so that I can set and monitor performance goals throughout the plant life cycle. So the interface here with PRA and GRA is so that you can set more aggressive goals for equipment and redundant equipment for those whose inability to perform the function results in the increased safety risk or reduced operational capability. In production space, it's the same like we do in safety space. We want to put the resources in the right place. So the advanced reactor community is challenged to assure high reliability economic performance right out of the box. And so it needs to be designed in. And the established systems and component level goals need to be achievable, or the design needs to change. So that's the other piece. The PRA and GRA can't say to the RAMI program, this is what you need to achieve. The RAMI program has to be able to say back, we can't get that kind of reliability out of the way you've designed the system, change the design. So it works both ways. There's 3 steps generally in the RAMI process. One is the qualitative evaluation. Typically it's done using FMEA and answering the question, what are the possible component failures and their effects. Now, there are other ways to do it. You can do single point vulnerability. You can do reliability block diagram. I've used HAZOP. I happen to like in some cases that's actually more appropriate to use. And you want to then talk about now the outcome, which is the functional importance and inspection, monitoring, and preventative maintenance activities in that qualitative space. Then there's the quantitative space, again, and we're using event and fault tree analysis. And you want to ask, how does the failure of a component affect the system and the plant? So now we're taking it a little bit higher level, making more an overall perspective, so that you can get estimates of the key metrics for safety. Again, interfacing and production, interfacing with these PRA and GRA models. These steps have been done for a long time. These particular RAMI steps do go back, to the 80s and 90s. What's changed is this last piece, this production analysis. And this is actually what's turned this into a much more powerful tool than it was before. It's relatively new, and it leverages computational advances in the methods and architecture since what was done in steps 1 and 2 were developed and applied. We can do this because we got the computers and we got the codes to do it. And it's a dynamic simulation model to facilitate decisions, not just for safety, but also business and economics over the life of the plant. And we at JENSEN HUGHES, we've applied this to a broad range of process facilities to support integrated asset management, as I said, risk-informed asset management from cradle to grave. So that's the new piece that in the past half a decade or a little bit more has really made this whole process of risk-informed performance-based design more than it used to be. Behind it is what we call the state model. This is the simulation model. It's a dynamic simulation model, and it provides analysis of plant production over time. It includes provisions for equipment failures as well as planned maintenance. So it evaluates that. It looks at, in a production setting, it accounts for the time a system or process may be idle, meaning that it's waiting for items fed from an earlier sub-process. That could be equipment, it could be any one of a number of things, supplies, etc. But it's helping you to understand what the potential for a system or process being idle could affect the plant performance. It's a statistical model. It samples from prescribed distributions, which may be based on data if available or expert judgment. I didn't mention expert judgment earlier. We understand these advanced reactors don't necessarily, maybe they only have data for 80% of the type of equipment that's in them, like buses and pumps and things that are common, we've had for a long time, but they also have some unique equipment. So you would use an expert judgment process in the design as you worked along, and you'd improve it as you worked along. And it outputs the estimates of production over time with statistical the detailed evaluations in support of investment decisions combined with econometric models. Application of the models in the early design phases will support development of robust and resilient designs that look at both economics and safety, because at this point in the process, it's easy. It's easy and cheap to find the choke points and design them away. It's when you get further along that retrofits are expensive. We can go to 17. So it provides essential information to support decision making, including the classification of the functional importance of the plant's SSCs with respect to all of these aspects. You can identify and prioritize actions that you can take to improve plant performance, areas where design changes would provide substantial benefits. Maintenance, specifying your maintenance, your predictive, preventive, and condition-based maintenance in order to achieve these goals for the SSCs. Identification and evaluation of alternatives to enhance the economics, minimize the cost. And the integrated monitoring process to make sure that you don't stop doing this when you're finished with the design and construction, you continue to carry this through the life cycle of the plant. And you have this framework to look at modifications to asset management, to plant maintenance, et cetera, throughout the cycle. So the bottom line is it provides information to decision makers to support informed decisions that consider all the various objectives of all the various stakeholders. Next one, please, Pat. So this is the process flow. that I'm not going to go into this in detail, but what I wanted to show you here is how it fits very nicely in the risk-informed performance-based process. You're seeing here those little blue boxes that are the other side of the interfaces that I showed in the earlier design chart. I had inputs and outputs on that process flow chart for RAMI, and here's where they go and come from, okay, as we're going through the process. So one way to look at it is the design process creates a wish list of performance goals for the design to achieve at the SSC level, and the RAMI process determines what's actually possible and feeds it back into the design process. We can go to the next slide. So what are the design issues addressed by the process? We've got the plant, the various activities and that you can do. What are you looking at? You're going to design, you're going to look at how can physical separation of systems help me? How can functional capacity of equipment help me? The basis and content of operations and maintenance procedures, what should be in them? How about the testability of equipment or systems processes? So let's see, corrective and preventive maintenance, including during operation, test inspection intervals. The allowed outage times for failed equipment, not just safety equipment, but again, you want to think of it in terms of how long is an allowable outage time for something that I need for production. If, for example, I have 3 feed water pumps, I take one out for maintenance. As long as I have it out for maintenance, I've increased the risk of a derate or from loss of another one. So the question then becomes, what is sensible for me for an allowed outage time for a feed water pump? That's an example. Various actions you can take to mitigate equipment failures, optional aids, and operation and maintenance training. Okay. Pat, am I still here?
Yes, we're on slide 20.
Yep. Okay, let's move to slide 20. Right. Okay. So the overall approach, then, the basis for design assessments and decisions of the plant models. I said that I would come back to this. The keys to successful application is that you need a structure that provides useful output as the design evolves. So you're going to integrate the modeling activities into the design process to keep pace with the design at the decision points. Use the automated computer tools, PRA, GRA, RAMI tools, to allow for easy iteration and look at the addressable parameters in the design decision process. Am I updating it every day? No. Am I updating it every 6 months? No, not either. Okay? There has to be a cadence, and as you reach certain things that you've added, you're going to say, I think this is something we need to look at, and we need to understand if we're headed in the right direction. So but it's important that they only reflect what's known at a given point in the design process. So they'll start out being simple and gain detail as the design process continues. And the decision at each point in the process will focus on the aspects of the design that are most difficult to change as the design evolves. So early on, you're going to want to do things like footprints, building footprints, barriers, things like that that when you get to the 60% or 80% design, you don't want to have to change that and start moving stuff around. So you do need to kind of figure out what are the right decisions to make at each point in the process based on what I know. And the model needs to include all modes and hazards. The next slide, we talk a little bit more about the model scope. So all modes, all hazards for the PRA. The GRA model needs to address all the ways in which capacity factor can be lost. This is the additional modeling that I talked about earlier where it comes into play. You can't use initiating event frequencies. You need to model the systems that lead to initiating event so you can design to meet the production goals. you need to look at the planned outages and how can the plant make these outages more efficient through things like fuel handling, equipment overhaul, maintainability, right? When I talked about maintainability of major equipment. You need to look at the unplanned outages, which effectively are the OK sequences in the PRA. You have to model all the normally operating systems, as shown here, right? Primary cooling, secondary cooling, water cleanup, anything whose failure can result in a shutdown or a derate. And then the administrative shutdowns, which is that interface between safety and production, where a regulation from the NRC says, if you get into this situation, you need to shut down, or you need to, and so because we want to remember that a safe plant is an efficient and a reliable plant. So we'll go to the next slide. The model will evolve through the process. Now, I've roughly listed the design phases as a concept, okay? But there's no really bright line. You don't magically go from conceptual from completed conceptual design, and then I go a completed preliminary design, and I learn nothing in between. It just doesn't work that way. And in fact, different parts of the plant could be in different phases at any given point in time. It may be, for example, that the NSSS system is more advanced. You're going to submit that to the NRC soon. But maybe the system to provide process steam, you're not quite as far along. Maybe not. So you need to think about the decisions you can make for different parts of the plant based on where they are in the design. And you're not making them all at one point in the phase. I don't say, all right, I'm going from conceptual to preliminary design. I go take a nap. I relax. When I get to preliminary design, I make decisions. As I said, you don't update it every day, but you don't wait 6 months or 8 months or whatever. You're going to ask yourself questions along the line. So this is just a rough, a concept laying out that you start early and you go through the entire process. The next slide, during each phase that the risk team is going to need to define what information is available and should be provided by the design team. They have to work together on this. They have to talk about where each part of the plant is in the design process, how far advanced is it, what kind of information can you give me, and then based on the information, what should be modeled. We have thought this all out. There's a much longer presentation. There's like a 3 or 4 hour seminar on this, and we talk about what can be modeled, what level of detail can you model at each phase in the design. You don't want to get ahead of the design. You want to stick to what's known and assume only what fits into that known envelope. How should you consider human factors and human actions, and what types of decisions can be supported given the state of the design? So this is my little line at the end that I always end with. There's a risk, a tendency to want to get more out of the PRA and the GRA, more out of the model than you really should. Then you're stretching it out. You're making assumptions that you have no basis for. So my favorite line: don't torture the risk model until it screams for mercy and gives you what you want. Make sure you are doing what makes sense based on your understanding of where you are in the design process. So that's pretty much it. I'm just about where I wanted to be. I wanted to be about a quarter of, so I'm a little bit before that because I wanted to leave plenty of time for Q&A. But that's where we are now.
Thanks, Paul. So there was one question in the chat, so I'll ask you the more specific version of this, and then while we're waiting on, it looks like we've got another one, but I did want to extend it past for security. So just two questions that are going to be related to security here. So the first one is a bit more specific. How does the GRA address cybersecurity?
Well, okay. I don't think it addresses it any better than a PRA does. Okay. those would come under other considerations that you have to look at, because as you know, and even in PRA space, we don't model intentional attacks on the plant, whether it be physical or whatever. That's just something to put a probability on a bad actor is something that I don't think anybody feels comfortable doing. So this is more, so that's got to be handled in the more traditional way.
Okay, thanks. Yeah, and I think that actually I was going to ask just in general, how much augmentation or modification would you anticipate in order to accommodate the incorporation of like a more performance-based approach to security? Like I know that the NRC has some new proposed alternative performance-based physical security requirements, but I think unless you wanted to add anything, I do think that kind of how you specifically how you answered it specific for cybersecurity, I think that also just applies in general to security. Is that right?
Yeah, and in fact, the ASME and ANS Joint Committee on Nuclear Risk Management is actually has a working group on risk and on performance-based, risk-informed performance-based security. But again, it's not quantitative. And they're working on that, and hopefully in the not too distant future, there will be a document issued on that. But it is still to a large extent based on trying to risk inform and performance based the vulnerability analysis that has typically been done.
Okay, great. Yeah, thanks. No, that sounds really interesting and useful work. You've got another question here from the chat. In addition to thank you for the engaging discussion and comments on how great it is. So the question here, some new reactor developers are considering failure modes and effects analysis, or FMEA, as an alternative to a probabilistic risk assessment model. So if an FMEA is performed to obtain risk insights, is PRA necessary for the process that you've described? So I guess specifically, can the process work without PRA as long as an alternative tool, for example, an FMEA, is effective in obtaining the risk insights that are desired?
As you saw in a couple of the slides I put, the FMEA in our mind is an input to the more comprehensive probabilistic model. That it's not capable of that holistic view. It's informative, but it's just one of like a half a dozen different inputs that you would use in a PRA and GRA. I don't think it is in any way a substitute for that.
Okay, thanks. Got another question here about the scope of the GRA. So where does the GRA stop? Does it go all the way to the thermal and or electrical delivery? Does this include balance of plant, non-safety equipment,
Yep.
pipelines, et cetera?
Yep, absolutely everything up until it gets to what it's serving. So, for example, if for electricity for a data center, it would be up until you're at the data center. So it would include that transmission, that whole thing. And then when it gets to the data center, then it's like you have your power. You figure out if you're reliable enough to use it. Okay. Similarly, in the case if it was Dow for the steam, it's like it would take it all the way to the steam is now at your plant. Okay. It would be then up to them to make sure to design their system to be reliable once the steam is received.
Great, thank you. Another question here about GRA in specific. It's about uncertainty. So how does the uncertainty propagate through the GRA, and how is it used to inform the final results? Is this fairly similar to how it's done for PRA, or are there different considerations here?
It is. No, it is. It's done pretty much the same way. And it goes into this decision process as a consideration for basically to help guide a decision. An example being, if I have two decisions whose mean, effect, are the same, but one has a much higher uncertainty than the other, I might say, oh, well, I want to do the one that has less uncertainty. The other thing it might drive you to is trying to reduce the uncertainty, right? What is testing for, right? What is testing, modeling, et cetera? So I might say, okay, I need to reduce the uncertainty, so I'm going to, like Kairos, I'm going to build a little plant, and I'm going to try to reduce the uncertainty in some of the performance aspects. Same thing with like what eVinci is doing with the NTR out in Dome. It's the uncertainty is unacceptable. We cannot build this and deliver it to someone with this uncertainty. Therefore, during the design process, we're going to do testing, we're going to figure it out, and then we will design in accordance.
Great. Yeah, no. And so I think even following up on that one, do you have some thoughts or some comments on how much data would be necessary to fill out a GRA relative to the more traditional PRA?
How much data? That's actually a kind of a good. It's going to depend on the design a lot, isn't it? I mean, I think about it now, is that some of these advanced reactor plants, their MSSS are so simple and passive and everything that perhaps the balance of plant will require more data. I'd say for a light water reactor, it might be the same or a little bit less for the rest of the plant, for the production, because again, some of the things you're going to put in your PRA, like your normal shutdown systems and things like that, are also production related. So it's going to vary. That was a very good question. I hadn't really thought about it, but it's going to vary depending on the design.
And speaking of varying applications, we also have a request here in the chat for any other examples of non-nuclear applications of this methodology that you might be able to speak to.
Yeah, well, I mean, we've done it for various process facilities, like chemical process facilities. We've done it for we've done it in the fire area quite a bit. We have done some work. We have done some defense-related work that I really can't talk about, but for processes, basically to try and do the same thing with regard to assuring that the defense facilities achieve their what we'll call production goals. So yeah, so we have various different applications that have been done.
Great. So Steve Cron, I know we got a couple different Steves. Those are the questions that we've got in the chat right now. I don't know if we're gonna wait on a few more to come out, but I don't know if you had any.
Brandon,
Prasad has his hand up, so
sorry.
Prasad, go ahead and ask your question.
Yeah, right. Thanks, Paul. Great presentation. Based on your working with people outside of the nuclear industry, do you use the term risk-informed, performance-based, or if you do use it based on your experience, do they understand what that means?
For some, that's what we use. For others, for others, in some cases, we just say RAMI. Okay, we'll do all the other stuff, but we call it RAMI because they understand that. They understand that concept. In some cases, we do call it risk-informed performance-based. In some cases, for some technical communities, we just say performance-based because for various reasons, risk-informed is problematic terminology.
So when you say performance-based to such people, do they have a common understanding of what that means?
Yes, Yes, they do understand that. They do understand the concept that of um, relief from prescriptive requirements. Okay, they do understand that what we're talking about is that performance-based means you are told what you need to achieve, not how you need to achieve it. That's how they understand it.
Well, that's very good to know, actually, because I think a formal definition of risk-informed performance-based would express that exact contrast. You know, that deterministic issues are mitigated by a probabilistic approach, but prescription is mitigated only by what I think of as a formal performance-based approach.
That's a good way to put it. Yeah.
Well, and one of the things that I'm trying very hard to do is get such a common understanding. And I'm trying to see how many people are aware that the Commission defined it very formally 25 years ago in the SRM to SECI 98-144. And, it's been a little bit of a mystery to me why people are not using something that was defined at the commission level. And therefore, the staff is in fact obliged to, use it. If an applicant presents a safety case based on that definition.
So, Paul, do the people who you work with who understand performance-based as a way to update requirements, have you seen them formally define it?
You mean like write it down a definition?
Yes.
I can't say that I have. It may exist in some of it's more of an understanding, I guess, is what it is. And the way we explain it is, let's look at this requirement and try to understand why it was written. What was it trying to accomplish? Let's dig back before somebody said this is the best way to do it, and say and dig back in and figure out what's the reason. Why did we think this was important? And then walk forward from there and say, okay, what other ways, alternative ways, are there to achieve that same intent?
Yeah, I like that. As if we could continue this conversation offline, and you could mention maybe some of the industries that are favorable to that approach. Maybe we could do some research and look, maybe we, meaning myself, Brandon, and the committee, could do some research on their standards base and see if they in fact have definitions that they work to. But excellent presentation, Paul. We really appreciate it. I enjoy the melding of safety and availability, production that this entails, and I think it's an important insight for the group. So if we don't have any more questions, I guess we'll give people back 3 minutes for their potential weekends, although you guys on the West Coast still have to work a little longer.
And people are welcome to reach out to me. Pat, do you have I think the last slide has my contact information on it. So you can reach me through that email address or that phone number or WhatsApp, text. And also, obviously, I mean, you can also just send it to Pat. Everybody has Pat's contact information, and she can forward it to me.
All right, Paul, thank you very much. Have a good weekend, everybody. Great attendance, and we will see you in several weeks.
Okay.
Cool.
Thank you.
Thank you, Paul.